Physical Science 20. This is the PW1.5 section, light waves, interference, and diffraction. So we looked at, in the last video, properties and speed of light, determining that. Now we look at some other things that can happen. So explain what is meant by incoherent light, coherent light, interference fringes, and monochromatic light, and explain how light falling on two slits produces an interference pattern. We look at objects that are illuminated by white light, such as a light bulb. You are seeing what is referred to as incoherent light, which is light that has unsynchronized wave fronts, which are out of phase. So on the bottom of the sheet, I kind of drawn that. So incoherent, they'd be out of phase. So we don't have crest meeting crest. If this wave and this wave are interfering, we can see here's a crest, here's a trough, and they are interfering out of phase. Also, they have different frequencies. So I could have a small frequency here, whereas over here a very large frequency. So out of phase and different frequencies. The effect of incoherence in waves can be seen in the example of heavy rain falling on a swimming pool. The surface of the water is choppy and does not have any regular pattern of wave fronts or standing waves. Because light waves have such high frequency, incoherent light does not appear choppy to you. Instead, as light from incoherent white light source illuminates an object, you see the superposition of the incoherent light waves as white light. So we just see an even white light, which is what you would see out of a light bulb. Interference and coherent light. The opposite of incoherent light is coherent light, which is light from two or more sources that add together in superposition to produce smooth wave fronts. A smooth wavefront can be created by a point source such as shown in the figure above left. A smooth wavefront can also be created by multiple point sources when all points are synchronized. So here we're looking at combining together. So we have in phase. So we have this wave that's meeting in phase, or a wave that's like that. So in phase, crest and crest, trough and trough. And also same frequency. So notice same frequency here. I don't have a high frequency and a low frequency. A smooth wavefront can be created with multiple sources when all points are synchronized, such as with a laser, as shown in the figure above right. Only the superposition of light waves from coherent light sources can produce the interference phenomena that we will see shortly, which is kind of related to the interference we saw with normal waves. English physician Thomas Young proved that light has wave properties when he produced an interference pattern of shining light from a single coherent source through two slits, just like when we had the two slit interference with constructive and destructive interference. When the overlapping light from the two slits fell on an observing screen, the overlap did not produce an even illumination, but instead created a pattern of light and dark regions, which Young called interference, or an interference pattern. So interference fringes. He explained that these bands must be the result of constructive and destructive interference of light waves from the two slits. Now this photocopy isn't the greatest, but if you look carefully here, you can see light, dark, light, so light area, dark area, light area, dark area, light. So one of those areas is constructive, destructive, constructive, destructive. Just like when we looked at the interference of just waves, water waves. It makes that pattern as well. We had those nodal lines, and those nodal lines result in a dark area. Constructive interference, or the antinodal lines, would be a light area on a screen. In a double slit interference experiment that uses monochromatic light, so by monochromatic, we just simply mean one frequency, which light is only of one wavelength or one frequency. Constructive interference produces a bright central band of the given color on the screen, as well as other bright bands, nearly equal spacing and nearly equal width on either side, as shown on this left. The intensity of the bright bands decreases as we go further from the center. So we can imagine like this is the center, and then moving out they get lighter. The intensity of the bright band decreases as we move further away. Between the bright bands are dark areas, which are destructive interference. The positions of constructive and destructive interference depends upon the wavelength of light. So look at that. So it can help us identify what type of frequency of the light will be. When white light is used in a double slit experiment, however, the interference causes the appearance of a colored spectra instead. Now, if you look at a PDF version of these notes, you can see that this is kind of a colored area. It has more of a rainbow type look. Again, brighter in the center, but moving out, it decreases in brightness. The interference causes the appearance of a colored spectra instead of a single figure or a single colored. All wavelengths interfere constructively in the central bright band, and thus the band is white. The positions of other colored bands result from the overlap of the interference fringes that occur when wavelengths of separate color interfere constructively. So the double slit interference to create coherent light, so light of one wavelength or one frequency and in phase, from incoherent light, such as white light, Young placed a barrier with a narrow slit. So if we imagine this is the light coming in, here is the barrier. This is kind of a three-dimensional diagram, and you can see there's one slit here. So if we have white light going through that one slit, we get this happening. So placed a light barrier with a narrow slit in front of the monochromatic light source. Because the width of the slit is very small, only coherent portions of the light passes through. In cylindrical diffracted wavefronts as shown here. Because the cylinder is symmetrical, the two portions of the wave arriving on the second barrier with the two slits will be in phase. So that ensures that they are in phase. Two slits at the second barrier then produce coherent, nearly cylindrical wavefronts that can then interfere. So again, the coherent light is in phase and of one frequency or wavelength. So they can interfere, very similar to how we saw before. Depending upon their phase, the two waves can undergo constructive or destructive interference as shown below. So if we imagine slit 1 and slit 2, the waves come together. These would be in phase because you can see crest, crest, trough, trough, and it makes a bigger crest and a bigger trough. If they're out of phase, we get destructive interference in some areas. A top view of the cylindrical waves from Young's slit experiment are shown below. The wave fronts interfere constructively and destructively to form the pattern of light bands. So the pictures that we saw over here, these over here, what that is showing is the resulting pattern of something that we've seen before. So very similar to water waves. We have the overlap here where a crest meets a trough. We have destructive interference, which in this case is symbolized by the dotted line. And we have constructive interference where crest meets crest and trough meets trough. So crest meets trough, crest meets crest and trough meets trough. We get a bright area where we have destructive interference, dark. So by looking at the pattern we could say this is a screen here, and you can actually do this with the laser. Shine it through two slits and you'll get a pattern like this, an area of, it's weird because we expect to see just two bands of light coming through, but no, it interferes, so we get bright and dark regions in a pattern. Brightest in the middle and then decreases in intensity as we go to the left and to the right, if I'm looking at it this way. Okay, so that was an experiment that proved that, hey, light has wave properties because it has a pattern that is similar to just regular wave interference when I have constructive and destructive interference. All right, so that is that section. It's kind of a tricky little part, just basically showing that light definitely has wave properties by looking at double slit interference. And you should be able to do the assignment now, and we'll see you again.